Hello, welcome friends. Welcome to our online lecture series. Today's topic for the discussion is work done by a varying force. In our earlier lecture, we had seen the work done due to a constant force. In today's discussion, we will be considering a derivation based on the work done by a varying force. Especially as a varying force, we will be taking an example of a spring force. For this arrangement, what we have considered over here it is. I have shown you the two diagrams over here. If you carefully look at these diagrams, you can see there is a one block which is kept on a horizontal surface. This horizontal surface I am taking it as an x-axis. Okay, this block it is attached to a spring, and this one end of the spring it is attached to the fixed vertical surface, and the other end of the spring it is attached to the block. Okay, as we apply certain force on this block, so what will happen, this spring will elongate, and as this spring will elongate, it will exert a restoring force on this block. Okay, and as you know that you might have studied in our in your 12th standard in the chapter simple harmonic motion, that whenever there is a spring, it exerts a force which is directly proportional to its extension or elongation produced in it. So if you consider, as you move this block away from this point A, so the elongation produced in the spring, it will be increased, and as a result of that, this magnitude of the force which is proportional to the displacement, it will vary. So x changes, force changes, that is why it is a varying force. So spring force is nothing but a varying force. So you just have to remember this is that for a given spring, the force constant I am assuming it is a k. So force exerted by the spring, it is F is equal to kx. So this is the understanding you have to keep with you from your earlier standard, that is simple harmonic, earlier standard chapter, that is simple harmonic motion. Okay, now let us start with the today's topic. So let us see. First of all, we will write the description of the figure, and then we will start with the actual mathematical expression. Okay, so I will just write down the description of the figure. The description of the figure, it is like this. Consider a block placed on horizontal surface. Here we are assuming that there is no frictional force, so you can write frictionless horizontal surface as well. So consider a block placed on horizontal surface. Consider a block placed on a frictionless horizontal surface. The spring is attached. The spring is attached to the block. Spring is attached to the block, and other end of spring is attached, is fixed, you can write, is fixed with horizontal support, rigid support, with a vertical, I am talking about this, so vertical fixed support. Vertical fixed support. Assuming that the spring constant of spring constant, assuming that spring constant is k, hence the force exerted by the spring force exerted by the spring on the block will be F is equal to K into X, where X is the displacement of the block or spring, where X is the elongation, we will say elongation produced in the spring, elongation produced in the spring. Okay, so this is the force. F is equal to Kx. So we have to remember this. F is equal to Kx is the force. Now, what we will do now, we have to calculate the work done during the motion of this block. So for this purpose, what we will consider, suppose initially the block is at the position A, where the displacement in natural position of the spring, this is the natural position of the spring, the block is at the position A, where there is no displacement. Okay, when we apply force on this block, suppose that after a certain interval, infinitesimal interval of time, the block moves from the point A to the point A dash. Okay, so we will write it over here. After applying a force, block moves from A to A dash during a small time interval. Okay, now the displacement of the block, it is A to A dash, which is nothing but the dx bar. The displacement which is infinitesimal small. Infinitesimal displacement is dx bar. The infinitesimal displacement is dx bar. Now, this displacement is very small because it is infinitesimal, because it is taken over a very small interval. So what we will assume is that as this displacement is very small, we had seen that the force is directly proportional to the displacement. As the displacement is very small, and so we can consider that over a very small interval, this displacement, it is constant almost. So as this is constant, so your force will be constant. The displacement is dx bar over this small displacement. Force is constant. Okay, so we are assuming that over this small displacement, this force is constant. Okay, now we have to calculate the work done by this force. Therefore, the work done by the force F, work done by the force for moving a block from A point to A dash, for A to A dash, is dW is equal to, now we had seen the definition of the work done. What is the definition of the work done? Work done says that it's a dot product of the force and displacement. So here in this case the force is F bar dot dx bar, F bar dot dx bar. Now we have to consider one thing over here. The force is, see, if you are moving a block is in this direction, if you are moving block in this direction, the spring will exert a force in this direction. The force by the spring, it will be in reverse direction because they are oppositely directed, because it is a restoring force. Okay, so if block is moves in this direction, the displacement is in this direction. So this is the displacement. You can say that this is your displacement. So displacement is in this direction and the restoring force is in this direction. So your force and displacement both are oppositely directed. So yesterday we had seen in our earlier lecture that if the force and displacement are in opposite direction, the angle between them is, if this is the case, then the angle between them is 180 degree. And we had seen the one work done in such a case, it will be negative. So as the force and displacement are in opposite direction, then theta is equal to 180 degree. So the angle between them, it will be 180 degree, and we had seen yesterday cos of 180 degree, it is 1 minus 1. Cos of 180, it will be minus 1. So what I'll do now, I'll just write down this work done. Now I'll write this work done as like this. I'll just erase this part. Okay. Now I'll just write the work done. dW is equal to force, it is F dx cos theta. So which is cos theta value is minus 1. So it is F dx into cos 180. So this will be nothing but minus F dx. This will be nothing but minus F dx. Okay. So this is equal to minus F dx. But we know that this force, just we had seen, this force F is equal to kx. So we can write it here, F is equal to kx. So it is minus kx dx. So this will come out to be minus kx dx. So this is the work done over a small displacement when the block is moving from A point to the A dash point. Now this is the work done. Now this we had taken over a very small interval, so it is an infinitesimal interval. Suppose though your block moves from the point A to point B. Suppose you moves from point A to point B, the displacement of the block is x bar. Okay, so now we have to calculate the total work done. The total work done when block moves from point A to B, from point A to point B. Now we have to calculate that work done. So I will write it that W is equal to, this will be nothing but an integral over A to B. A is this position where the displacement is 0 and at B point the displacement is x1. So what we can write it is integral over dW from x is equal to 0 to x is equal to x1. X is equal to 0 to x is equal to x1. And what is value of dW? That is minus kx dx. Minus kx dx. X is equal to 0 to x is equal to x1. X is equal to 0 to x1. So I can rewrite this. K is constant. I can take it outside. So it is minus k. Integral of x will be x square by 2. So this will come out to be 0 to x1. It will come out to be 0 to x1. From this one I can rewrite this. First of all, put the upper limit, which is x1. So it is minus k in a bracket x1 square divided by 2 minus lower limit, which is 0. So it is minus minus plus k, 0 divided by 2, it will be 0. So your total work done in this case, it will be minus 1 by 2 kx1 square. Minus 1 by 2 kx1 square. This will be the total work done when our block moves from the point A to point B. Okay. So you just have to consider that the work done depends upon the what is the final and initial position of the block. Okay. Now what we will do, we will try to calculate now work done. See, with this work done we have considered when block moves from point A to point B. Okay. Now what we will do, we will just consider a general situation. General situation in what sense? We will start from one point. We will start from one point and we will go to the another point. Okay. And from that point we will again come to the original position. Means for like this. We will start with the point x1. From x1 we will go to the x2, and from x2 again we will come to x1. Okay. So we have to consider a work done over a round trip by this spring force. Means for example, our block starts from the position x1, we will stretch it up to x2, and from x2 again we will reach at the x1 point. Okay. So we have to consider the work done over a around the journey, over a single oscillation, you can say. Okay. So we will write it here. Similarly, the work done to move block from position x equal to x1 to x equal to x2. Okay. From x equal to x1 to x equal to x2. So I'll write down that work done as W from x1 to x2. Work done from x1 to x2. So instead of this integral x is equal to 0 to x equal to x1, my integral now it will be from x1 to x2. Integral will be from x1 to x2 dw, which is minus kx dx. Minus kx dx. This is equal to, this we can rewrite. We can rewrite. Okay. Minus k will be constant, so we will take it outside. So this will be minus k. Integral you will get x1 to x2 x dx. We will get x dx, and this we will rewrite as minus k into integral of x. It will be x square by 2. It will be x square by 2, and limits of the integration is from x1 to x2. x1 to x2. Okay. First of all, we will substitute the upper limit and then lower limit. This we can rewrite as minus k in a bracket. Upper limit is x2. So it is x2 square by 2 minus lower limit, which is x1 square by 2. Okay. And if you remove this minus sign and if you take 1/2 outside, so you can rewrite this as 1/2 minus becomes plus. So we can rewrite 1/2 k x1 square minus 1/2 k x2 square. I have just opened the bracket and given this minus sign inside the bracket. Okay, so this term will be minus, which I had written secondly, and this minus becomes plus, which I had written initially. Okay, this is the work done when an object moves from the point x1 to x2. Okay, similarly, the position is changing now. We have to go back now. Okay, that is in this step we had gone from x1 to x2. Now we will go in reverse direction from x2 to x1. Okay. Now if the block is brought back to original position, that is x2 to x1, the work done is, now we will write it over here, w from x2 to x1, because now we are moving our block from x2 to x1, so w from x2 to x1, this is equal to integral x2 to x1. What is w? It is minus kx dx. Okay, minus kx dx. And again we will use the property of an integral. What we will do, we will change the limits of the integral. Or you can just simplify this straightforwardly. You can write minus k in integral. Here it will be x dx. It will be from x2 to x1. This is equal to, now if it is minus k, in bracket integral of x will be x square by 2. So it will be x2 to x1. This is equal to, so this will be minus k in bracket, first of all put upper limit, that is x1 square by 2. x1 square by 2 minus lower limit, that will be x2 square by 2. So this is equal to, now what we will do, we will give this minus k and we will separate out this term. So this minus, this plus becomes minus. We will write it down in the second term. So it is 1/2 k x1 square, and this minus becomes plus. So this we will write it first. It is 1/2 k x2 square. Now what I will do, I will call this as an equation 1. I will call this as an equation number 2. Okay, I will just call this as an equation number 1 and I will call this as an equation number 2. Okay, so now what we have to consider a work done around the trip. That is, work done around the trip means we have bringing back the block again to the original position. So the work done. Okay, then if we add these two equations, equation number 1 and equation number 2, adding equation 1 and 2, adding equation 1 and 2. What do you mean by adding equation 1 and 2? If I add these two equations, so LHS will be w from x1 to x2 plus w from x2 to x1. So this is equal to, now see, if we are saying that w from x1 to x2 means we are moving block from position x1 to position x2, and in the second case we are bringing back block from x2 to x1. So now what we have to consider is that we are moving from a one point x1, we are going to the another point which is x2, and again we are coming back to the x1 again. So it is a work done during a round trip. Okay, work done during a round trip. So we will add this. What is equation 1's RHS side? It is 1/2 k x1 square minus 1/2 k x2 square plus, what is this? 1/2 k x2 square minus 1/2 k x1 square. Now you can see 1/2 kx1 square minus 1/2 kx1 square, this will cancel, this minus this plus will cancel. It means that work done from x1 to x2 plus work done from x2 to x1, this is coming out to be 0. This work done is coming out to be 0. So from this one we can say that the work done, this means that the work done during the round trip by spring force is 0. Work done by a spring force around the trip is 0. So this is the derivation which we were about to discuss today, which we had discussed earlier now. And we had seen that work done during a round trip by spring force is 0. So this is actually having a very good physical significance in the coming lectures. So actually we will be coming next lectures we will be discussing what is conservative force and non-conservative force. For these definitions and for these concepts we will be requiring these examples. Actually the work done by the spring force round the trip, it is 0. It means that it is a conservative force. Okay, this we will be discussing in the coming lecture. Thank you.